Hello viewers, in today's session we are going to discuss an important application of vectors, and in this class we are going to prove an important result or theorem in Euclid's geometry. So here using the concept of vectors we have to prove that parallelograms on the same base and between the same parallels are equal in area, right? So let us start. Now let us draw the figure here. So the diagram goes like this. Let us consider a vector A, and here we can take this point as O, and this point O may be taken as origin, and here we can take the point as A. Now let us consider another vector here. This vector may be taken as vector B, and this point may be taken as B, right? So let us complete this parallelogram. So here we have this parallelogram, right? And this point may be taken as C. So we have the parallelogram OACB, where the adjacent sides are represented by the vectors vector A and vector B, and this point O may be taken as origin. Now let us draw the second parallelogram, and here we can draw the parallelogram like this. So this is our second parallelogram. Here we can draw a parallel line to this one, and here we can complete or we can extend this vector, that is vector BC, to the point E, right? So here we can take this point as the point D. So we can now have another parallelogram OAED, right? And the first parallelogram was OACB. So these two parallelograms are on the same base, that is OA, and between the same parallel lines or same parallels, that is BE and OA. So now here we have two parallelograms. The first one is OACB. OACB. The second one is OAED. So here we have OAED. Now these two parallelograms are on the same base. So the same base is given by this vector, that is vector OA, and these two parallelograms are between the same parallels. So the same parallels may be taken as this line, that is BE. So we have this vector BE is parallel to this vector OA, right? So this is the situation. So here we have to prove with the help of vectors, that is the area of this parallelogram, that is parallelogram OACB is equal to the area of the parallelogram, that is OAED. OAED, right? So to prove that these two areas are equal, we have to make use of some concepts from vectors, and the first concept is the scalar multiplication of a vector. So let us first consider this parallelogram OACB, and let the vector area of this parallelogram OACB is denoted by vector A1. So vector A1 represents the area of parallelogram OACB, and we know that the area of this parallelogram OACB is given by the cross product of these two vectors, that is vector A and vector B, right? So the area of the parallelogram OACB is given by the vector product of vector A and vector B, and the direction of this vector, that is vector A1, is perpendicular to the plane containing vector A and vector B. And now we have to show that the vector area of this parallelogram OAED is also A cross B. So now first consider this point D, right? Now see the points B, D and C are collinear, and this is an important concept here to prove this result. Now this point D lies between B and C, so that the points B, D and C are collinear. And when we have collinear points, then this vector, that is vector BD, can be represented by the scalar multiple of the vector BC, right? So here we can represent this vector BD as a scalar multiple of the vector BC. So here lambda is a scalar, and lambda belongs to the set of real numbers, right? So the vector BD can be represented as a scalar multiple of the vector BC, because due to the definition of collinearity of points, we can write one vector as a representation of scalar multiple of other vector. So now from this parallelogram OACB, we can easily see that the vector OA is vector A, and the vector OB is vector B. And since the opposite sides of a parallelogram are equal, so this vector, that is vector BC, is equal to vector OA, and vector OA is vector A, right? And this vector BD, this vector BD can be represented as vector OD minus vector OB from by using the triangle law of vectors. Because if we take this triangle, that is the triangle OBD, then by triangle law of vectors we have vector OB plus vector BD is equal to vector OD, right? So here we can now write vector BD is equal to vector OD minus vector OB. So that's why we have written vector BD as OD minus OB. So here we have lambda times BC, and BC is vector A. Now here we have vector OD, and OB vector can be taken as vector B, and here we have lambda A. So OD vector can be written as the lambda A plus vector B, right? So taking this minus vector B to the right hand side, vector OD is now equal to lambda times vector A plus vector B. So now consider the vector area of this parallelogram, that is OAED, right? So let us denote the vector area of parallelogram OAED by vector A2. So this is the area of parallelogram OAED, right? Now we know that in vectors the area of a parallelogram is given by the cross product of the adjacent sides. So here the adjacent sides of the parallelogram OAED is given by OA vector and vector OD, right? So we can now write a vector OA, and here we can write vector OD. So the area of the parallelogram OAED is given by the cross product of the adjacent sides. So the adjacent sides are OA vector and OD vector. Now OA vector is given by a vector A. So here we'll write vector A, and here we have vector OD, and we have already expressed this vector OD in terms of vector A and vector B. So let us write vector OD as lambda A plus vector B. So now we have to find out the cross product of vector A and this vector, that is lambda A plus vector B. So now to find out the cross product of these two vectors, we'll make use of the distributive property. And the distributive property says that if we have a vector A and if we take the cross product with a vector, say vector B plus vector C, then we can write vector A cross vector B plus vector A cross vector C, right? So here we have the similar situation. So now we can write vector A cross lambda times vector A plus vector A cross vector B, right? Now here lambda is a scalar, so we can now write lambda, and here we have A cross A plus A cross B. So here we see that we have the cross product of same vector, right? And from the properties of vector product of two vectors, we know that if we have the cross product of same vectors, then this is a zero vector, right? So here we have lambda and zero vector, and here we have A cross B, and lambda times 0 vector is 0 vector, right? So we have 0 vector plus A cross B, and this is equal to A cross B, right? So the addition of A cross B with the 0 vector gives us A cross B, and A cross B is the vector area of the parallelogram, that is OACB. So here we can write the vector area A1, right? So we see that the vector area A2 is equal to the vector area A1, right? So viewers, this is how by using the concept of vectors we can prove that parallelograms on the same base and between the same parallels are equal in area. And remember the vector area, that is vector A1 or vector A2, the direction of both these area vectors is perpendicular to the plane containing vector A and vector B.